Hi, everyone. In the last couple of episodes, we introduced the notion of binomial coefficient and choose k, which is n factorial divided by k factorial divided by n minus k factorial. And its meaning is the number of ways to choose an unordered set of k objects from n objects. The important thing is that these k objects be unordered. If we reshuffle them, we don't count this as a different way of choosing them. Today we'll practice more with the notion of binomial coefficients, and here's our first example. How many ways are there to divide 20 students in a debate class into two teams? A pro team and a contra team. Evenly, 10 students in each team. The team have different roles. One team is supposed to defend a certain thesis, and the other team, the contra team, is supposed to challenge that thesis. How many ways are there to divide the class this way? There are 20, choose 10 ways. Why? Because in order to divide the class, we just have to choose the students for the pro team. Once we know that these students go to the pro team, the other students, the other 10, will automatically go to the contra team. We don't have to choose them. Therefore, the number of ways to divide the class is 20, choose 10. And that is, if you compute it, is 184,756 ways. A similar example, but a different one, is how many ways are there to divide 20 soccer players into two teams with no particular roles ascribed to each of the teams. It's 10 students in each team. These teams have no roles. And so if, let's say, these 10 girls go here and these 10 girls go to here, that's one way. And if we do it this way, we don't count it as a different way. For us, it just matters how the girls are split. The roles of the teams are the same. And so over this number that we computed in the first part overcounts the number of ways by a factor of 2. We count this and this as two different ways, and we shouldn't have. So the answer should be divided by 2 to ignore the order between the teams themselves. And that number is 92,378. Today we came to one of the most famous examples in the probability theory, one about the lottery. To play a lottery, one needs to pick 5 different numbers in any order from 1 to 69. And also another number that's called a Powerball between 1 and 26. So all in all, you pick 6 numbers. If all of these 6 numbers match the winning combination, the winning numbers in no particular order, you win the grand prize, the jackpot, $100 million, something like $500 million maybe. What is the probability to do that? how many ways are there to play the lottery? How many ways are there to choose 5 numbers from the 69? That's 69, choose 5. On top of that, you'd have to choose a number between 1 and 26. And so you multiply this by 26, because for any choice of the 5 numbers, you still have 26 choices for this separate number, the Powerball. And that's a number of ways to play, 292,201,338. Of all of these many, many ways to play the lottery, only one way is the winning one. It's a jackpot. You need to match all these numbers. There is only one way to do that. Number of ways to win is just 1. And so the probability of jackpot, the probability of winning in this game is 1 divided by that huge number. And that's the answer. Disappointing, isn't it? For instance, this probability is 50 times smaller than the probability of you being struck by a lightning this year. Another situation where you can win the lottery is to win a smaller prize. And maybe that is more likely. Let's do this. What is the probability to guess correctly? Exactly 3 numbers. And not the jackpot. In this case, you get a minor prize of $7. Quite smaller than the jackpot. Okay, again, how many ways are there to win that prize? Imagine this is our universe of numbers and a jackpot. Here we include all 69 numbers that are possible. Again, just remember the rules. In this lottery, you have to pick 5 different numbers from 1 to 69 and 1 jackpot. So there are 69 numbers, out of which 5 are winning. And the rest, 64, are non-winning. And the Powerball only has 1 winning and 25 non-winning numbers. Now, in order to win the minor prize, you need to guess 3 winning numbers, which means that we will have to choose 3 numbers from the bucket of winning numbers, and the rest 2 should be non-winning. Remember, we are to write the 5 numbers. So 3 are winning, the rest, the 2 are non-winning, and we want to not win the jackpot this time. So we'll choose 1 number from the 25 non-winning jackpots. How many ways are there to do that? First of all, how many ways are there to choose the 3 winning numbers from 5? That's 5. Choose 3. How many ways are there to choose 2 non-winning from the 64? That's 64, choose 2. And we multiply these numbers together, because for any choice of the winning numbers, we still choose 2 non-winning in this many ways. And furthermore, we need to choose 1 number from the 25 non-winning Powerballs. And this is easy. 25, choose 1, but I can just write 25. We know it's 25 ways to choose that 1 number. This is a number of ways to win. And we still need to divide this by the total number of ways to play, which is this 69 choose 5 times 26. Number of ways to play. And that is our probability. That is the answer. And the answer, if you compute this, would be 0.017. So that's the answer. 1.7% of winning the minor prize. One more example. Imagine that a lab has 100 rats, 40% of which are sick, so 40 sick rats, and 60% are healthy. Now we take a sample of 10 rats at random for a test. We would like that the sample be representative. So what is the probability that the sample also has 40% sick rats? The same percentage as in the general population of rats in this lab. Such a sample we may call a representative sample. A picture will help in this problem too. Here's our lab, and this lab has 40 sick and 60 healthy rats. We would like to choose how many sick rats do we want to choose? Choose 4 sick rats, and we want to choose 6 healthy rats. In this case, our sample will be 10 rats with the same composition of sick and healthy. What's the number of ways to select a sample? Well, we're selecting total number of ways to select a sample, regardless of whether they're sick or not sick. We're just choosing 10 rats from 100 rats. So 10 choose 100, choose 10 is the answer. What's the number of ways to select a representative sample? The representative sample is selected by choosing 4 sick from 40 rats and 6 healthy from 60 healthy rats. And we multiply this because for any selection of the sick rats, there are this many ways to select the healthy rats. So the probability that the sample is representative is the ratio of the valid ways to select the sample, the representative sample, over all ways to select the sample, which is 40 choose 4, 60 choose 6, 100 choose 10. And the answer is 0.26. So about 26% is the chance to select a representative sample. It's not very promising, right? Only 26%. We would like this to be better. You can do better by allowing yourself a little bit of a room instead of exactly requiring that the sample have exactly 40 sick and exactly 60% healthy. You can require that the sample has, let's say, between 39 and 41% sick. Just allow yourself some room for the error. If you do that, then the probability increases, especially if the number of rats increases in the lab. This is guaranteed by one of the main results in probability theory called the law of large numbers, and also the central limit theorem makes it more precise. We will get to these results in the future. Stay with me. Have a good day.